Right. Well, thank you. I'm going to pick up a little bit on what we just heard in terms of the influence of light elements in the inner core, but this time thinking about the influence on the physical properties. And this is a follow-on really from a talk that Arwen Duyss gave a year ago reporting the seismic data of the inner core. And I've been thinking a little bit more about the links between the mineral physics properties of iron in the inner core and the seismic data that we obtain, or our seismic colleagues obtain for us on the inner core. So from seismic observations, it's clear that the Earth's inner core is elastically anisotropic, and this has been known for quite a while, that rays that travel in polar directions travel faster than, for VP, than those that travel along the equatorial directions. But there's also evidence now, and this has also been accumulating for some time, that attenuation in Earth's inner core also shows directional as well as spatial variation. And so the theme of what I'm going to say is really how to interpret these in terms of what's going on at the atomic scale within the inner core. So this is the result that Arwen Duyss obtained back in 2010 from normal mode analysis of anisotropy of the inner core. So both normal modes and body waves show fast velocities in polar directions, slow velocities in equatorial directions. And this has been used, this concept, to understand the inner core in terms of texture. So the typical interpretation of such information is that the inner core is highly textured, and these sorts of data would fit with an anisotropic inner core which is made of textured, for example, Hcp iron. But you could also actually get textured cubic FCC iron to match this to some extent as well. But with Hcp, it would be clear that we'd have a dominant texture growth with the z-axis parallel to the polar axis, and this makes intuitive sense. We have the symmetry of the system matching the symmetry of the crystalline state. What's also been seen over the years is that the attenuation of seismic waves through the Earth's inner core is also anisotropic. And this has been seen in body waves, but now more recently in the paper by Mäkinen et al. To be shown also by normal modes. And this changes our understanding. This result changes our understanding quite a bit, because up to this point, the body wave data had been interpreted in terms of anisotropy and scattering. So the attenuation was interpreted as the scattering of waves. But the normal mode data are on a length scale that's much greater than that of potential microstructures in the inner core, and would be most highly reflective of the intrinsic physical properties of the material, rather than scattering of the rays. In other words, the attenuation here is due to the intrinsic damping properties of the solid, the crystal. So body waves show attenuation anisotropy, as do normal modes. And they show that, so these data show that for the P waves, the attenuation anisotropy is greatest along the polar axis, and for S waves, it depends upon the polarization of the S waves. So S waves that are polarized equatorially show little attenuation. Those that are polarized with their polarization vector parallel to the meridian show a greater anisotropy. So normal modes have wavelengths much greater than that of the estimates of the inner core grain size, so would be insensitive to grain boundary scattering. This is not a scattering process. So it suggests that the anisotropy of the attenuation is the intrinsic property of the crystalline inner core. And so how can we resolve this? How can we link this to the potential properties of an alloy in the inner core? There are a number of possible causes of intrinsic attenuation, intrinsic mechanical damping of crystalline solids. So one would be stress-induced ordering of interstitial atoms. So if we have, this is what makes iron with a little bit of carbon in rather a good damping material. This is why it's used in the bases of lathes and milling machines. There could be damping due to dislocation microstructures within the solid. There could be damping due to grain boundary viscosity, or due to phase boundaries, phase transitions between polymorphs. For example, if there's a phase transition between FCC and HCP, or FCC and BCC, then we'd expect to see, due to the interface between the structures, some damping. I'm going to rule out straight away, I believe, grain boundary viscosity. If we take the estimates of the size of crystals within the inner core is growing at 0.5 millimeter a year. It's got a very low thermal gradient. It's zero gravity at the center, clearly, and it's almost perfect crystal growth conditions. So estimates for grain boundaries, for grain sizes in the Earth's inner core, range from tens of meters to hundreds of meters or more. In this case, the volume of grain boundary is vanishingly small as a proportion of the total volume. On the other hand, dislocations may be predominant, pervasive, and we know that light elements are incorporated in the inner core, maybe up to 5%, we heard in the last talk. As far as phase transitions are concerned, phase transitions would also induce potential damping mechanisms, and this is the phase diagram of iron-nickel at ambient pressure. We know that the iron phase diagram is very sensitive at ambient pressure to carbon, to other solute atoms. And so there are potential transitions between structures. But also, Zenner pointed out in the 1930s that all of these different processes may induce different damping peaks as a function of frequency in the system. So we might have damping due to grain boundaries. We think this is unlikely in the inner core. There may be damping due to pairs of solute atoms or to interstitial atoms, or to dislocations, or to interfaces between twin boundaries. But the most common anelastic, that is mechanical internal friction or inverse quality factor source in iron at the Earth's surface, as produced in the iron foundry for the iron workers, is the SnBr relaxation in body-centered cubic metals. So this has been studied extensively in the 1950s and 60s. If you put a solute atom like carbon, nitrogen, or oxygen into a BCC iron structure, then it will sit in the octahedral interstice here, which isn't quite an octahedron, because along the z-axis, this distance between the next ion is a upon 2, but in the 1, 1, 0 direction, it's a upon root 2. So this interstice has tetrahedral symmetry. That means that if you put an interstitial atom in that position, it will cause a small distortion on that site, and that distortion will have tetragonal symmetry. That means the z-axis will change slightly. So now if we apply a stress, you can accommodate a strain by switching to a different interstitial position. So if we apply a stress to one of these unit cells, that atom will just jump to the neighboring interstice, and in doing so, it will generate a strain. And that strain will be an anelastic strain because it takes a little bit of time for that jump to happen. So there's a diffusive jump that is producing a mechanical loss. And measurements of this sort of process show that you get these, this is inverse quality factor here effectively, you get peaks due to jumps that depend upon the chemistry of what's going on. So this is for the oxygen atom, this is for the nitrogen and the carbon atom. So if you have a range of alloying elements within your crystal, you'd expect a range of overlapping mechanical loss processes. But what about HCP iron, the favored structure of the inner core? In hexagonal close-packed iron, the interstitial positions are the tetrahedral interstice and the octahedral interstice. And here we have a problem because both of these sites have a trigonal symmetry down the z-axis. They have effectively the same crystal class type shape as that of the structure itself. If we put an interstitial atom into HCP iron, it doesn't distort the symmetry of the structure. So to have a system where we have a distortion of the structure that generates a strain, we actually need a pair of interstitial atoms. And this is seen in real synthesized alloys of HCP metals. And it occurs because the pair of interstitial atoms can form an elastic dipole. So here, this pair of interstitial atoms are sitting either in two tetrahedral interstices. We apply a stress, and we may flip one to a neighboring interstice. And in doing so, we modify locally the chemical bonding and the chemical strain. So there's a potential for developing strain with pairs of interstices. The second interstitial atom could flip into the octahedral interstice as well, and you'd have the same effect. Now, this only becomes important if you have enough interstitial atoms to have pairs. And this then becomes a statistical problem, and it turns out that the limit by which you begin to see this effect is around about 1%. So if you have 1% interstitial atoms in your structure, you begin to see sufficient pairs by probability that you would get a measurable anelastic effect, a measurable internal friction. And this has been seen in the past in HCP metals. So here's an example. This is hexagonal close-packed yttrium with interstitial hydrogen. And the interstitial hydrogen flips between these sites and generates a peak in the inverse quality factor. And the peak along the z-axis is much bigger than that along the basal plane, the xy axis. So this begins to fit with the observations made by seismic studies, that the anelasticity, the damping along z, is bigger than that along xy. And actually, it depends upon composition. So as we increase the amount of solute atom in the structure, we increase the damping. It also depends upon temperature and on frequency, and it behaves in an Arrhenius fashion over many log units. We've done similar things in Cambridge on iron germanium-based alloys. When you put a large proportion of germanium into iron, it actually adopts a hexagonal structure, and you begin to see this same Zener relaxation in the hexagonal structure. People have also looked in the past at the influence of dislocations in hexagonal metals. And so this is the influence. This is data from 1984 on the Bordoni peak. This is a magnesium single crystal, a hexagonal close-packed crystal that had been cold worked to generate a large number of dislocations. And when you measure the anelasticity in this material, it varies anisotropically with orientation, but the orientational dependence is opposite to that's seen in the seismic data, assuming that we have a texturing with z-axis parallel to the polar axis. And indeed, the damping that's seen in magnesium would suggest that it would favor movement where dislocations are in the basal plane. Because we only have one slip system in hexagonal close-packed structures, dislocations only move in the 001 plane, and therefore we don't have significant damping perpendicular to that plane. So for that reason, it would appear that dislocation damping is unlikely to be significant. So we're left with this other possible process, phase transitions, and there are phase transitions in iron of martensitic type transitions where we generate phase interfaces between the polymorphs of iron. This may be a polymorph between FCC and HCP, or FCC and BCT, body-centered tetragonal or body-centered cubic structures. And these interfaces would also be susceptible to stress. We can move these variants by applying a stress, and these are examples that we've measured of iron-nickel alloys as a function of temperature. And when you do this, these high anelasticity peaks occur at the phase transition and not away from it. So this, if it showed up in the Earth, would show up as a narrow region of damping, a narrow region of attenuation at a particular depth. So this signature hasn't been seen so far in any of the data seismically, as far as I'm aware. So that leaves one remaining candidate for the intrinsic attenuation in the inner core, which is this stress-induced ordering of interstitial pairs of atoms. And so in summary, what we can do is we can look at the intrinsic attenuation in the core and potentially get a measurement of light element heterogeneity, because the amount of attenuation depends upon the composition, depends upon the extent of substitution or interstitial site occupancy within the structure. It's inherently anisotropic in the correct sense, so the attenuation in an anisotropic crystal is inherently anisotropic because the moduli, which are the complex components of the elastic constant, are a tensor, a second-rank tensor in the same way as a fourth-rank tensor in the same way as the elastic moduli themselves. And it would provide a potential route to discriminate between structure types in Earth's inner core. And as far as HCP is concerned, it would seem that Zener pairs are the most likely candidate for the relaxation that's seen. Thank you.
I have a question. So when you do the numerical simulation about the light atoms in the specific area, can you also simulate something like the atom clustering?
Yes, I think this would be, so the question was, can you simulate atom clustering in computational simulations? And I think this is the obvious way to approach this question now, would be to look at the influence of pairs of atoms locally on the structure, and also the jump rates, so the dynamics of switching an interstitial atom from one site to another.
Okay, one more question.
Can you rule out partial melting to explain attenuation?
So I haven't discussed the depth dependence of attenuation, and there's observations also of depth dependence away from the inner core outer core boundary, which could be attributed to partial melting. But the attenuation that's seen is predominant in the P wave along the polar axis, and there you begin to then have to invoke particular microstructures to explain it, which become more complicated, I think, than the fact that you do have inherent solute atoms in the structure.